Welcome to the discussion on the topic of concept of pure bending. This is a part of unit 3, namely flexural stresses in beams, or sometimes it is also named as pure bending in the course strength of materials 1. Now I am hoping that by the end of this particular discussion the learners will be able to relate to the concept of pure bending and what is its significance, and able to rephrase the bending equation as required for the analysis and design of members subjected to the pure bending phenomena. Now coming to the definition of pure bending, in general when you load any beam, uh, the beam is generally subjected at any point, a cross section if you take it is generally subjected to shear force and bending moment, assuming that the loading is perpendicular to the longitudinal axis of the member. You take this is the longitudinal member. Generally, beam is meant for that, right? By to carry the transverse loads. So, assuming that the loads are acting in the direction perpendicular to the length of the member or the longitudinal axis of the member. So, if you apply such loading, then obviously what are the forces acting on the beam? The forces acting on the beam generally are shear force and bending moment. Now we should load the member in such a way that no it any part of the beam is subjected to only bending moment. There is no shear force. If you could able to load the member in such a way that either part of the beam or full of the beam, which is not possible, completely total bending is not possible. So at least a part of the beam, if it is subjective to bending moment and there is no shear force, no such a what you call kind of loading where the beam is no subjected to that kind of force system, design forces where only bending occurs and there is no shear force, then the beam is said to be under pure bending, right? So what has been we are here specifically pointed out is there is a constant bending moment in a particular segment of the beam. Constant bending moment should occur and the shear force should be zero. There is no shear force. So shear force is zero at a particular cross section and bending moment is constant. Then we will say that that particular beam is in pure bending, right? For example, now this particular person, an athletic, or sorry, you can say a person weightlifter, he is lifting a weight. You can see. So whatever may be the the size of the weight of the weight is that lifting, it doesn't matter for us. What is matter for us is when he is lifting like this, this part of the member, you see, treating that this is one support of the beam and this is another support of the beam, and the person who is acting, let's say this is the load that he is applying on that. Okay, if we invert that particular beam, right, that becomes this kind of beam, right? This one, when you invert it, this look like this. This is the support here and this is the support here, and these two are the loading here. So when that situation happens where two loads are acting like this, okay, and these two are the supports that we are able to see here, then what happens if you construct a shear force and bending moment diagram for this case? Now you will be getting shear force here P, right? What is the shear force here? Shear force of the beam and the support is P here, right? This is P. Similarly, the shear force here is P. So if you draw these shear force, you will be getting here a positive shear force here and there is a negative shear force here, because both are upwards, right? This is upwards and this is also upwards reaction P. So when you construct, you will get a shear force like. Now if you draw the bending moment, so what will happen? You will get a shape like this, because this is P. So P times your, let's say this is L and this is also say 2L. You can say any length, doesn't matter. So then what happens? This is PL, right? This part of the bending moment, and also this part is also PL. Now you can observe the center part, right? The between the loads. What's happening? The shear force is becoming zero, whereas the bending moment is constant. So this is the case we are referring to now. This is what we are calling it as pure bending. When a portion of the beam or segment of the beam wherein only bending moment, right, constant bending moment occurs and there is no shear force at all, such a part of the beam is said to be in pure bending, in the state of pure bending. Okay, same thing. If I take a cantilever beam and I apply a moment m here, then if I try to construct the shear force diagram, it is a straight line. There is no shear force at all, because there is no load, right? Moment doesn't create no external moment on in a cantilever, does not create any shear force. Shear force will be zero. Bending moment will be constant. So this part of the entire, or you can say entire part of this cantilever beam is in pure bending, right? So a cantilever subjected to external couple, right, as well as a simply supported beam subjected to symmetrical point loads from either ends. Both the beams are subjected to pure bending. Remember here, this, it doesn't matter that the beam is supposed to be having zero shear for throughout the beam, which may not occurring in many of the cases. So even if part of the beam is having zero shear force and having constant bending moment or bending moment, you can say, if it is consisting the having only bending moment, there is no shear force, that part of the beam is said to be in pure bending. So this may be no possible in many of the loading cases. It is possible that shear force can be zero somewhere, and therefore the bending moment can exist there, therefore the pure bending can be applicable, right? So it need not that entire beam is said to be only in bending moment. Then the application of the pure bending will be limited. So that is not the case. Even wherever you can find this situation, the particular part of the beam there only bending moment exists, then such part of the beam can be considered to be subjected to pure bending. Now we will try to see what are the governing equation for the pure bending concept. So before having before deriving that particular um, equation, governing differential equation, let us see some of the assumptions that are made to eliminate possible type of confusions, so that we can smoothly derive the derivation, or you can just simplify the simplify the process for the development of the governing differential equation, right? So these conditions must be satisfied in order to apply the your pure bending concept. So what are these? Let us have a look at it. Beam is initially straight and unstressed. So it should be a straight member. Okay, beam should be a straight member, unstressed. So one may ask that why, anyway we are not loaded, right? When it is loaded, it gets stressed. So he is saying unstressed means, that means there is a situation possible where even without applying uh, loading, there is a possibility of beam get stressed. Okay, for example, when one of the supports is settled down, then there is a possibility of that particular beam is subjected to some additional moments even before application of the loading. So there is some kind of pre-existing stress available. So that case we cannot apply this. So it should be straight and unstressed. The material of the beam is homogeneous and isotropic, right? So it should be, the material should be of same material should be available, right? Homogeneous throughout the member, and it should have a identical properties in different directions. Okay. Then the loading, how far you can apply the loading is loading whatever you are applying, that should be within the elastic limit. It should not go beyond the elastic limit. Then plane cross sections plane before and after bending. So what this saying is, if there are, if you consider, let us say, when you apply some load, the what you call, the fibers, they are getting, let's say I have some loading here. This is the beam and I am applying. Just a second. Um, so this is a beam, let's say, and I apply some loading. What happens is it bends. Let's say this is the beam, so it bends like this. So what he is saying here is, yep, according to the distance from the neutral axis, say this is the neutral axis, we'll see. Some people might not be having idea about the neutral axis. Neutral axis is that, in simple terms, you can say that is no, that is neutral. It is neither compressed nor stressed out. In other words, neither tension nor compression. So there is one neutral layer here. That from that neutral layer, the displacements will be proportional to the distance of the fiber. So that's what the meaning of. In other words, strain variation is linear. The meaning of this particular assumption is the plane cross sections remain plane before and after bend, means the strains are linearly varying, right, proportional to its distance from the its distance means fibers distance from the neutral axis. And the beam is, the next one is, beam is made up of number of layers which are free to expand or contract independently. That means each layer is treated as independently. Okay, it doesn't have no any influence over the another kind of. So we make this assumption, although it may not be practically correct, right, but for the sake of simplification we made this assumption. Next is Young's modulus velocity of the beam material is same in tension and compression. That means whatever you are getting the Young's modulus value in tension, also same as Young's modulus value in compression, right? This must be satisfied. And radius of curvature of the beam, right? The radius of curvature beam is very large enough comparison to the cross sectional diameters. So suppose it bends, right, the radius in the form of some kind of a circle, right, or some kind of an arc. So that particular radius of curvature that of that particular beam is very very, um, uh, high value compared to the cross section. Maybe out of the cross section either B or D. Compared to those B and D, depth and width, that is very high value. So let us consolidate all these assumptions, right? Here, if you, make into one cluster, some of the properties are talking about the materials. For example, second one, material of the beam is homogeneous and isotropic. Then Young's modulus of the beam material is same in tension and compression, right? Then rest of the things, if you look at, they are talking about the beam, right? In the sense, beam is initially straight and unstressed. The other things, these are talking about the layers. So plane cross sections remain plane before and after bending. This is also about the layers. Beam is made of number of layers free to expand or contract. Then finally about the radius of curvature, right? So you can classify in order to make them more by hand, to remember by hand. You can make them into some cluster and then you can remember, right? So then next one is how you can get to the derivation of the governing differential equation for pure bending. Look at this. Our target is to calculate the bending stress. For that sake, what we are taking some cross section. Let us cut two cross sections. Our entire focus will be on that only now. So this is the beam, right? Beam cross section, say having some particular length. This is the length, of course. So you can have uh, uh, this is the length of, it's longitudinal axis, the neutral axis, right? Neutral axis means I just now told that there is no compression or tension or no stress. It is a neutral layer. Okay, so we have a neutral layer here, and we cut off we have considered a cross section by cutting the beam into two locations, say HE and GH. At two locations I cut off the beam. Now on this, what I am doing is I am marking one particular layer. My interest entire further calculations will be on this particular layer. I am interested to calculate what is the bending stress at this layer. Okay, on this layer, what is the bending stress? So let's consider, as I told you, CD, if the center of the beam, which is called neutral axis of the beam, which is neither compressed nor stressed. Above that, at a distance y, you consider a layer, say AB. Okay, so now our entire focus will be on this particular layer AB only. So this is before loading. Now as soon as I apply some loading. So if I apply some loading, such as this kind of loading, if I apply loading, then obviously I am just applying moment from the downward side like this. Then obviously the whole beam go upwards. Right, when the beam go upwards such as this, then the points that we have marked on these fibers, they also get distorted. They go to the different location. For example, if you look at but here is an interesting point. As we told earlier, we have made an assumption that before and after bending, plane sections remain plane before and after bending. So HE and these two are parallel now, right? So that's what he is saying, remain parallel. H dash E dash and G dash F dash, just as HE and GF are parallel before bending, even after bending also H dash E dash and your G dash F dash, they remain parallel to each other, right? So in the process, what's happening is, once it is bent in this form of an arc, so you can connect that part of the beam and through radial lines and connect them to its center. So you form a subtending angle theta. Let that radius maybe r, right? This is r, and the subtending angle between the two cross sections that we have considered is theta. So in that case, I am interested now to calculate for this fiber, because this is the layer I am interested. So I want to see what is the amount of strain that is developed. So remember, here in the derivation, our primary concern is to calculate the strain. From the strain, these are the three steps: strain calculation, then come to the stress calculation, then come to the moment equation. Because ultimately we are interested to calculate what is the amount of movement developed, because that's what we are applying. So finally we want to calculate the moment capacity of the section. Okay, so let's start the first step, that is calculation of strain, where in this fiber only, in this AB. So let us start that. In the fiber AB, I am trying to calculate the strain. So how to get the whatever the change in the displacement happened, change in the length that's happened in the length in the fiber AB, then to the original, whatever the original length divided by the, or the ratio of the ratio to the original length, right? So A dash B dash is the new position after application of the moment here. So it take a new shape. So this is your final position of the fiber minus initial position of the fiber is AB, which is available here. So A dash B dash minus AB by AB. Now I am trying to simplify this. See, AB and C originally before application of the load, AB and CD both are equal, right? And of course CD doesn't, C dash D dash is as good as CD only, because as we told, this is a neutral layer. Neither this is subjected to compression nor it is subjected to tension. Therefore this C dash is as good as CD only, right? These 2 points you have to know. Now our equation, in place of AB I can write the term CD, right? So let's substitute that. Then what happens? Your AB place you got your CD or C dash D dash. Okay. So here once you got this, let's see what is A dash B dash. Even here in this case, here also you can write C dash D dash, right? This is also C dash D dash. Now only two things we require, right? One is A dash B dash, another one is C dash D dash, right? So what is this? Or you can even say CD, right? So what is A dash B dash? How to get from this particular subtending angle? Because we this is an arc length. For this, treating this as an arc, right? For this, where was this A dash B dash lying? It is at a distance of, because from the neutral axis to the center of the circle, the distance is r. Above that, this distance is y. We mark that. This is our y. Right, just as we marked here, this is y, and up to here it is, so it is up to here, no, it is r. So total distance of this fiber A dash B dash is r plus y times theta, because length of the arc is radius into subtending angle. So what is the total radius? R plus y up to here. So this is the distance, whole distance is this, right? Sorry, this one, right, from here up to here, here to, what was the distance? R plus y, right? So this is the distance, r plus y times theta minus, now this one, it is simply either AB or C dash D dash, where it is exactly on the neutral edge. So this is distance is r only, we marked that. So this arc length, if you want, it's simply r times theta. So substitute both of them. So r plus y times theta minus r times theta divided by r theta. So upon simplification, what you are going to get is y by r. So you have got now the strain in the fiber that we are interested in. The fiber we are interested in is the AB fiber, which has been no, stressed upon the application of the load. It has taken a new position A dash B dash. So change in the length of that particular strain in that particular fiber is nothing but change in the length by original length. Change in the length is nothing but A dash B dash. The original length is AB divided by AB. So finally you got, we have expressed A dash B dash in terms of R and theta, right? So finally you got y by R. So this is the amount of strain developed in the fiber AB. Once you got the strain, it's easy to get the stress, because we have the Hooke's law applicable here, because it is an elastic limit. Therefore you can say stress by strain is Young's modulus, and you got here first equation, that is epsilon is y by r. Now you got your stress as Young's modulus times, because this is comes from the Hooke's law, E epsilon. Therefore what you got is Ey by r straight away, right? So this is your this epsilon is y by r, so you are getting E y by r. This is equal to E y by, so rearrange the terms, you will be getting sigma by y times is equal to E by r. So this is half part of your bending equation. Okay, let's move. So what was the next? So as I told you, the first step is strain calculation in any one of the layer, in the cross section. Then second one is stress, that also you completed. The last one now moment carrying capacity. Further, what I am doing is I am trying to consider one arbitrary cross section. So taking an arbitrary cross section, you mark the neutral axis here. Let us take one rectangular strip, no, along this cross section anywhere. So preferably at a distance y, as we take for a sake of, because we already taken that fiber at y distance only. So same y distance you can take one rectangular strip. Okay, they consider an rectangular strip at a distance y from the neutral axis, and the depth of that particular strip is say dy, right? The strip width, okay, or depth, you can say depth of the strip at this distance is dy. Now let's what you call continue with the previous stress equation. So we got this equation sigma equal to Ey by R. Now what I am doing is, in this particular strip, because I have to reach, I am at sigma now, I have to reach to M. So what is the process? We want to get no M, you in between there is force. From force you have to calculate moment, right? So sigma we have with us, so simply multiply from sigma. How to reach to the F? You multiply with the strip area. So take the strip area, you will get the what is the force on the strip. You first you calculate. So force in the strip is nothing but sigma times delta A. So this is a small strip, the area of that particular one will be y delta A by R. Okay, so y delta A by R, delta A is nothing but delta A is equal to, so this sigma is E by R, of course. Sigma is, we have already done, right? Ey by R. In place of delta A we are writing delta A only, right? So Ey, so later we will be writing converting this, right? As of now we are not doing anything with the delta A, sorry, right? um, so sigma is nothing but Ey by R and delta A written as it is. Now go ahead with the moment calculation, because once you got the force, right, you calculate the moment. So how to get the moment? We are calculating moment with respect to neutral axis only. So let's multiply with the distance from the neutral axis. So what is the distance of the strip? To get the moment, you have to multiply with the perpendicular distance. You have calculated force in this particular strip, right? So now you simply multiply with the R. So means with y, the strip distance, right, to the neutral axis. So you got sigma delta A is the force multiplied with y, right? So you already got Ey by R delta A into y, so that means Ey square delta A by R. Now just a little bit no, rearrange the terms. What I will do is, I will E by R I will put little outside, because the constant, the varying parameter is y square delta A. So for a small strip you got this delta A. If I want to get this thing, and for the entire cross sectional area I have to simply sum up all the fibers. Okay, so for that I can either use integration or I can use sum of them. So this sigma y square dA, or you can say integral y square by dA, either way you can, because it is integration also representing the summation of the particular entire area, right? So y square dA, what is this y square dA? It is, if you look at this, this is second moment of area, which is nothing but moment of inertia. So when you simplify this y square delta A terms becoming moment of inertia for you finally, right? Next, once you got that, so next thing is, you know you got this as in this place I. So just rearrange your terms. We got now M equal to E by R times I, because integral y square dA or sigma y square dA is nothing but moment of inertia or second moment of area. So rearrange the terms now. So you will be getting m by I. Now you can put this I here. You will get from this, you will be getting m by I equal to E by R. This is second part of the equation. Okay, this is the second part of the equation. Already we got sigma by y equal to E by R. So you can equate these two, because they are no same. A equal to b and b equal to c, then a equal to b equal to c, right? So you can put in that format, you will be getting your governing differential equation for the pure bending. So that was the proof of this particular pure bending, right? So let's see now what was each term, because this is important to understand. Finally, after getting this equation, each term is to be clearly known for them in order to apply them for a particular situation. So when you are doing problems, if you are clear of what is each term, then it is very easy for you to solve any type of problem on this. So let's look at one by one term in a close manner. So what is y? Y is nothing but we have considered on fiber, right? AB fiber from the neutral axis, right? This is the neutral axis here. From this neutral axis we have the considered layer. AB is the layer under consideration. So that is your y, distance of the layer considered from the neutral axis. Then what is your sigma? Sigma is the wherever y you have taken, there we have calculated your bending stress. Then what is moment of inertia? Moment of inertia, if you look at, no, moment of inertia is here. With respect to this, we have calculated the moment of inertia. This is the axis, right? Say I-axis. This is your I-axis. And this I-axis is will be, usually loading will be vertical. So I-axis will be in the y direction and I-axis we are using. That means what is that you have to consider here is moment of inertia of the beam cross section about neutral axis, right? It should be always with respect to the neutral axis, but what direction, that is also important. It should be perpendicular to the application of the load. So if the loading is acting in y direction, you take Ixx. If the loading is in x direction, you take if the loading is y direction, take Ixx. If the loading is in x direction, take Iy. So that is understanding about I and the radius of curvature. So this is straightforward. So and then modulus of velocity of the beam. These are constant anyway. Okay, that will be provided, or you may be indirectly has to be calculated sometimes, right? So these are the specific details of this particular each term in the bending equation. Now, if you look at the problems, whenever you are looking at the problems areas, you are basically coming across two types of problems. One is of analysis type, another one is of the design type. Okay, so here in the case of analysis type of problems, how we will be giving the questions based on analysis type and design type. If you understand, it may be very useful while handling the problems on this particular concept. We have two parts in the equation, right? Sigma by I, sigma by y equal to, or you can say m by I equal to sigma by y. This is the first part of the equation. Number of applications are available on this term, in this two terms only. There is another part, right? That is say sigma by y equal to e by r, or you can say three ways, right? You can write this equation, you can write in three forms. Sigma y equal to my by one format, and the equate first second we have equated. So first third we can equate, or second third we can equate. That means sigma y equal to e by r, or you can also write e by r equal to m by I. The applications of this first one is very dominant in analysis and design type of problems, right? These are the other two terms. The applications of that is somewhat limited. Okay, there are problems dealing with that, but very limited. Now that's why I am trying to focus presently on this particular first term only. What are the types of problems we will be handling just with the help of this particular single equation? Okay, one single equation, but have a lot of that. Let's see. So sigma by I equal to m by y, right? So analysis type of problems, there will be problems given in two different ways. One is you may be asked to find the permissible bending stresses, right? But that means he is asking find out the sigma permissible bending. Then what you are supposed to get supposed to know by that, you require m, you require I, you require y. So what is the terms that are dealing with I and y? It is nothing but simply cross sectional details b and d. If you know, then you can get this Iy. Then if you want your m, which is bending moment, you require the span of the beam, as well as you require the loading on the beam, type of loading, whether concentrated load, point load, whatever it is. So if you know all these details, then it is possible for us to find the bending stress. That's why you require loading, you require span, you require cross section. Span and cross section details are required to get to the permissible bending stress value. to be found out. If other way of giving this is, you may be asked to find the bending moment capacity of the section. In that case, you require sigma and you require z. Z is nothing but I by y, also you can write. Later on we will be dealing, this is called section modulus. Later on we talk about this. So z, or in place of this you can even write temporarily, presently you can write as I by y. So this particular I by y, right, you require sigma and I by y, then it is possible to find the moment of resistance. So for sigma you will be generally provided, because the based on the material you will have a particular sigma value, and cross section is also required. Then the cross section is, then you can get the I by y. So that's why permissible bending stresses and cross sections are to be provided to get to the value of moment carrying capacity of the section. This is also another category of problem in analysis type. Finally, design type. Now, when you want to calculate the cross-sectional details, right? That means you may be left with I as unknown, because once BD is not given, you cannot get no I. So therefore, I may be unknown. In those cases, what you're supposed to know? So the person who is interested to calculate this, he must have these values. That means M and sigma. Permissible bending stress is required. Then to get to the M, you require load and span. Minimum details has to be provided. Then it is possible to calculate bending moment. Load and span are given, you can get the bending moment. And when permissible bending stress is given, yes, you can get it. So in that case, you are supposed to calculate your cross-sectional details. That means either B, both B and D, if it is a rectangular beam, or if it is a circular beam, you may be asked to calculate the diameter. Okay, so these are the type of the problems which comes under pure bending concept. So with this basic understanding, now you are ready to handle any type of problems that comes in pure bending. So that's all about this concept of pure bending and its significance. And what was another one that we have kept right in the beginning? How we can use this for the analysis and design members subjected to pure bending. Thank you. That's all about the concept of